is I want to talk a little bit about what we can do with linear programming. So we've started talking about some constraints. So I went through, I think, one of the constraints for the movie theater yesterday. There's a lot more we can do in terms of those constraints. If there's time at the end of class today, we will go back and do a little bit more along those lines. But for now, what I want to do is talk a little bit about the versatility of integer programming. So what's nice about integer programming is you can do a lot of things linearly that might not seem linear. So versatility of integer programming. So the following is a list of things that we can do, all in the confines of integer programming. All right, so I'm just curious to see if it's working or we're having massive tech failures. All right, so things we can do. Now I want to try to keep them in the same order. So we can do products of polynomials. These will have to be real valued polynomials, but we can actually find a way to make products of polynomials linear. We can do binary indicator variables. So what this means is we can have something that will tell us 1 if a condition is true, 0 if a condition is false. You know, really nice cutoff. We can do OR statements. And then let me try to do things in statements. We can do both kinds of ORs. So does anybody know the two different kinds of OR statements? Yes?
Inclusive and exclusive.
Inclusive and exclusive OR. So inclusive OR means they can both be true. Exclusive OR means at most one of them is true. And since at least one of them has to be true, exclusive OR means exactly one of them is true. Other things we can do is we can do, I'll try to get the order in the same order. We can do if-then statements. We can do truncation. We can do maximum and minimum. We can do absolute values. We can do all of these within the confines of integer linear programming. This should seem miraculous. Why should this seem miraculous?
A lot of those things don't seem linear.
I'm sorry?
A lot of those things don't seem linear.
Okay, do a little bit stronger than a lot.
None of those.
None of these things seem linear, right? Some of them seem very nonlinear. The absolute value function is nonlinear. The maximum minimum function is nonlinear, right? Yet somehow we can handle all of these within the confines of integer linear programming. So when you first see this, this should make you feel like a convert to integer programming. And it should make you feel like this is the way to look at life. This is the techniques to use. Yes?
By linear, do you mean like linear algebra, linear equations, or like order linear operations?
I mean, I can phrase this within the confines of a linear programming problem.
Okay.
So I will have linear constraints, linear objective function.
Not necessarily linear runtime.
Not necessarily linear runtime. And that's exactly the issue. Are you in CS as well?
Yeah.
Yes. And so for those of you who are in CS, you know, there's 3 letters and 2 symbols. I will let you choose which subset of those symbols you want to use and which order you want to put those symbols. All right? And so there's a huge issue in terms of how long it takes for these things to work. So unfortunately, just because we can set it up as a linear programming problem does not mean that we can solve it efficiently. And that's the difficulty, is when we try to do this integer linear programming, the runtime becomes quite bad. We have algorithms that can often get us close to the solution, but in terms of being able to prove that we can get to the solution quickly is very hard. One of the other things that's very difficult about integer programming is that sometimes the optimal integer solution is nowhere near the optimal real solution. So right now I'm not going to go through the knapsack problem. This is done in the book. This is done in my notes. where if you look at the optimal real solution, and you look at the optimal integral solution, where you have to buy integral amounts of the weights, the optimal integral solution is nowhere near the optimal real solution. It's not just taking a small tweak of that. And that's what makes things so difficult, is that the integer solution can be very far away from the optimal real solution. All right, so the question is, how do we go about handling all of this stuff? Not surprisingly, the more things we develop, we can start to use these things to express the more complicated functions in terms of these other ones. So there's a trade-off here. We end up having something that works in the framework of linear programming, but we're introducing a lot more variables and some very difficult constraints, and that is going to affect the runtime. But it gives us something that will work. And so most of the time, this is a good trade-off. Okay? So let's go through a bunch of them. So let's start off with, I think, the binary indicator variable. So binary indicator variable. So we want z to equal 1, just so it's the same way as my notes. If a is greater than or equal to 0, z equals 0. If a is less than 0. So I just want some way to just quickly tell if a certain condition is true. Okay, so a is going to be some quantity. And I want a quick check. If I give you a quantity, is it hard for you to tell if it's greater than or equal to 0? No. So we just want a way to formalize this. And so I'm going to make some assumptions for today. And so these are not severe assumptions, but they will make life easy. Assumptions. 1. All quantities are bounded. And I'll often write maybe the absolute value of a is less than or equal to n sub a to indicate a bound that depends on a. And 2, all quantities are discrete multiples of delta. So the possible values are 0, plus or minus delta, plus or minus 2 delta, plus or minus 3 delta. How severe do you think these assumptions are? So the first is I'm assuming all quantities are bounded. Do you think this is a severe assumption? If anybody has infinite amount of financial reserves, please talk to me after class. I promise you, you won't miss anything. All right? The fact that things are finite is not a huge assumption. I'm not saying it's a small finite number. I'm just saying it's some finite number. I'm working in a compact set. What about the discreteness? How do you feel about that? Yes?
Are these the sort of assumptions that are necessary to use, or are they just, like, does it make our...
It's going to make our lives a lot easier.
But they're not necessary.
I believe you can do all this stuff without these.
Okay, sorry.
And as a nice exercise, try to see if you can remove them. It's going to make things a lot cleaner. Yes?
When you say all quantities, you mean all entries in our matrix A, all...
Everything we see in the world is discretized.
So it depends on what's the size of D.
So D is going to be like 10 to the negative quadrillion. So your Walmart, how do we measure your revenue? How do we measure your quantities? I'm sorry? Dollars. And typically, what kind of quantities are we talking about? Billions of dollars. Now, if we get to individual products, we might have products that are measured in dollars and cents. If I have delta to be 1 over 1,000, that should be more than enough for anything that Walmart is going to be dealing with. And again, when you have a big company, you could have some things that are being sold in maybe units of 1 over 1,000th of a cent. Because if the volume is sufficiently large, that will matter. Yes?
So saying delta is basically redefining our integer to the scale.
Exactly. Can anybody think of a product that is not sold in multiples of cents? Gas, right? How much is gas? $3, 31 and 9/10 of a cent per gallon right now, I think, on Route 2, something like that. Yes, it's 9/10 of a cent. Yes.
Is it 1 delta for the whole problem?
So I'm going to assume it's 1 delta for the whole problem. I only have finitely many deltas. I will assume that they're all commensurable, and I can get something like that. And again, this is an assumption. We can remove this with a little bit more work. It's just going to make things a little bit easier for us in terms of life. Okay, so now I want to start talking about the very first one. So I want z to equal 1 if a is greater than or equal to 0, z to be 0 if a is less than 0. So I need to introduce some constraints. Now over here, I'm not telling you what a is. Maybe a is some quantity related to what we're looking at. Maybe it's a combination of revenue we're going to be getting from movies. And maybe I'm trying to see how much revenue am I getting at a certain amount of time. Maybe I'm trying to estimate what is the demand going to be for a certain movie depending on what other movies are being shown. It's some quantity that involves the variables in play. So if you want, a is some function of the matrix, the vector x, maybe something like that. Okay? It's some long involved expression. And here are the 3 assumptions. I assume z is in 0, 1. 2, I'm going to assume a divided by na plus, I think, 1 over 2 delta, over 2 na is less than or equal to z. And 3, I'm going to assume z is less than or equal to 1 plus a over n sub a. So I'm adding these 3 constraints. One of these constraints is very different than the others. You're playing Sesame Street now. One of these things doesn't belong. Which is the one that's different? 1, 2, or 3?
Is that, sorry, is that
Yeah.
a1 or a prime?
Where?
For 1, z is in,
0, comma 1.
oh, I'm sorry.
I was up late responding to emails. My writing may be a little bit messy. Which constraint looks very different than the other constraints? The first one. This is the one that is the most severe. It forces z to take on integer values. And in fact, only the values 0 or 1. This is the worst constraint. It completely changes the nature of the beast we're looking at. We no longer have real values. We no longer have continuity. If you look at the proof we did, and again, I want to go back. We spent a lot of time on the simplex method. We had these dials. That's how I like to view it. And we would adjust things, and we would flow. Well, now, as soon as things are integer, can you flow by an arbitrary amount? No. You can only move in discrete amounts, and you may not be able to move at all. It comes crashing down. Fundamental obstruction completely destroys the problem. Okay? Constraint 1 is horrible. What about constraint 2? Is this very different than stuff we've seen before, or is this essentially the same as what we've seen before? It's essentially the same. There's one difference between this and what we say in canonical linear programming problems. What's the one difference? Yeah, we have a greater than or equal to. We always assume we have things of the form ax equals b. And now I have a greater than equal. Well, I can introduce a slack variable. I can introduce another variable and get rid of this. In the interest of exposition, I'm not going to express this in terms of the way we would for canonical linear programming. We can do that later. I'm choosing to present it like this to emphasize the key points. At the end of the day, how many of you think you will be using this by hand? Good. All right. You do not do this by hand. You use a computer to do this. I want you to see what a computer can do, and I want you to see what the costs of these approaches are. But you would never do a calculation like this by hand on any problem that's worth doing. Okay? And similarly, 3 is not so bad. So why does this work? All right, so let's look case 1. A is greater than or equal to 0. So if a is greater than or equal to 0, what does condition 2 tell us? Does condition 2 tell us anything about z? So what are the possible values for z? 0, 1. What do we want z to be if a is greater than or equal to 0? We want z to be 1. Is z equal 1 consistent with 2?
What is n sub k?
What do I? Maybe do I want a 2 over here? So n sub a,
That's the bound.
yeah, in fact, just to make my life easy, I'm going to overinflate a little bit. Just so I can keep my constraints a little bit simpler. I'm going to assume 4 times a is less than or equal to n sub a.
Why did you choose 4?
I just want some big number just to make life simple. Otherwise, I have to make my constraints a little bit messier. I'm choosing n sub a to be large, much, much larger than any value of a. If you want, let's make it even better. 100 plus 4 times the absolute value of a. This way I don't have to worry. Maybe my n sub a is 0. Right? What if the absolute value of a is 0? Then over here I've got n sub a is 0. When I write constraints like this, I've just divided by 0. I'm in the basement, no one can really see us, but that's a bad thing to do. So just to keep yourself safe, it's not bad to assume something like n sub a is at least 100, it's at least 4 times.
Why are we sure that we don't have to worry about some sort of weird office space around out here scenario in assumption number 2?
Over here?
No.
Or here? Well, I'm just making this assumption that all quantities are discrete and they're all multiples of delta. I'm just choosing a unit to measure everything.
But it's not possible that the deviation could accumulate that way.
I'm not sure what you mean by the deviation. Think of it as I'm measuring things in cents, and I'm measuring how much oil I'm shipping in 1 over 100 of a unit of oil. I'm choosing some scale to measure everything. And so I'm just choosing a discrete scale. I'm choosing to measure oil in, say, 1 over 100ths of a unit. I'm choosing to measure dollars in 1 over 100th of a unit. I'm choosing to measure distances that I'm shipping things in 1 over 100th of a unit. Every quantity I'm looking at, I'm starting off on the same kind of scale.
Right, but let's say you have hundreds of thousands of transactions and you lose a fraction of a cent each time. Or you're,
What do you mean by I lose a fraction?
You're off.
I'm a mathematician. This is a theoretical.
You're off optimal by a fraction of a cent.
I'm not optimal.
You're off, yeah.
Right now, we're not talking about optimal. I'm just talking about all quantities are discrete. So right now, I'm not trying to optimize. Right now, I'm just saying I'm assuming all my measurements are discrete multiples of something. And this is just the scale in which I'm measuring things. Anybody know the gravitational constant? I'm sorry?
Capital G.
Capital G, not little g. Little g is about 9.8 meters per second squared. Capital G, 6.67, I think, times 10 to the negative. No, 10 to the 23rd is Avogadro's number. So big G, the units for that, it's either -7 or -11. It's been too long since I've done this. And the units are strange units. There's what's called the rationalized metric system. In the rationalized metric system, do you know what the speed of light is? 1. Do you know what Planck's constant is? 1. They choose units so that some of the key quantities become 1. Okay? Think of it, that's what we're doing here. We're just choosing our units of our measurements so that everything has been put onto the same scale. Was there a question?
Got it.
Okay, yes.
So I guess kind of to follow up with what Greg was asking, there are no errors because everything is exactly an integer multiple of.
Yes. Later on, we can talk about how serious these things are, and you could almost surely generalize this, but this is going to make the exposition a little bit easier.
Can you explain the second constraint?
Which one? This one?
No.
This one? Yeah, that's what we're doing right now. Okay, that's what we're trying to do right now. What does this mean? Let's try to think about what's going on. If a is greater than or equal to 0, how large could a over na be? What's the largest this could be? At most a quarter. How large could delta over this be? At most a half. Imagine delta happens to be the size of n sub a. This is going to be at most a half. This is going to be at most a quarter. How much is this whole expression going to be here?
Delta have to be like at most A.
I'm overinflating. I'm being generous, right? This is not, the left-hand side here is never going to be greater than 1. Okay? The left-hand side here is never going to exceed 1. Because it never exceeds 1, this is not going to give me a contradiction. If the left-hand side equaled 5, I'm in trouble. Z's got to be either 0 or 1. If the left-hand side is 5, I'm in trouble. There's no choice of z that will be valid. But because the left-hand side is at most 3/4, we're going to be okay. Yes?
So, where does n sub k come from?
N sub a. It's the largest value that, it's related to the largest value that a can take on. So to be safe, I'm going to assume that my quantity a is such that 100 plus 4 times its magnitude is always at most n sub a. I'm just choosing n sub a to be a huge number. If I chose n sub a to be the largest value this could take on, this could actually be 1 over here, and this could be a little bit more than 1. I want to make sure that doesn't happen. So because of my assumptions, this quantity on the left-hand side is going to be strictly less than 1.
Yeah, I mean, I guess my question is why can delta be bigger than A?
Delta can't be bigger, well, delta cannot be, well, a could be 0. And if a is 0, then delta will be bigger than a. Delta cannot be bigger than n sub a. It's not going to be bigger than that quantity.
Wait, if a is 0, this is not a problem, it makes no sense.
No, I mean, I'm trying to define a indicator variable to be 1 if a is greater than or equal to 0, and 0 if a is less than 0.
But if a is 0, what does that even mean?
Just it takes on the value 0. Maybe it's the revenue, and I'm getting no revenue because I have nobody coming to see my movie. So a is just some quantity. If you want, think of a as 3x12 plus 4x45. Maybe this is related to some kind of weights of things on a chessboard. Or think of a as maybe how many squares have been attacked by a given queen. It's some quantity that we care about. I have some expression. I don't know what that expression is, but I have some expression. And so over here, I want to just have some kind of quick way to tell, is this quantity positive? Is it 0? Is it negative? So let's look and see what happens if a is greater than or equal to 0. If a is greater than or equal to 0, what does 2 tell us? What do we know about the left-hand side of 2? Is between 0 and 1. It's got to be greater than 0, right? Because even if a equals 0, delta will be positive. The left-hand side of 2 is going to be a positive number less than 1. So it's a positive number that's less than 1. What does that force us to have true about z? What does that force z to be? It forces z to be 1. Is there a question?
Another notation question about your handwriting.
Okay. So it's a positive number less than 1, so it forces z to equal 1. So forces z to equal 1. So if a is greater than or equal to 0, condition 2 forces z to be 1. Let's check condition 3. What does condition 3 do? So I want z to be less than or equal to 1 plus a over n sub a. Well, what can you tell me about a over n sub a? If a is greater than or equal to 0, this is greater than or equal to 0. So this is true for all values of z. So in this case, 3 is always true. So if a is greater than or equal to 0, what do we now know about z? So thus, a greater than or equal to 0 implies that z equals, I think somebody said it implies z equals 1. So does condition 3 have anything going on when a is greater than or equal to 0? If a is greater than or equal to 0, does condition 3 matter at all?
It's just consistent.
It's just consistent. It's along for the ride. Where do you think condition 3 is going to matter? If a is less than 0, condition 3 is going to kick in. Okay? When a is greater than or equal to 0, condition 3 is always true. Condition 3 is true if z is 0. Condition 3 is true when z equals 1. It's very nice. Condition 2, however, condition 2 is the key condition here. Condition 2 forces z to equal 1. All right, so this was the case when a was greater than or equal to 0. What's the next case? So case 2, a is strictly less than 0. So now let's look at what's going on. A is less than 0. If a is less than 0, what's the largest a could be if a is less than 0? Not minus 1, you're close. Minus delta. So a is at least minus delta. That's the largest a could be is minus delta. And if a is minus delta over na plus delta over 2na is going to be negative. So if I take the largest value of a that I can have, if a is negative, the left-hand side is negative. So no matter what, the left-hand side is always negative. So I have a negative number is less than or equal to z. What does condition 2 tell us about z? Not much. I will tell you the following. On the upcoming midterm, everyone will get better than negative 1/2 on my midterm. All right, you're welcome. I couldn't say this at the beginning of the semester, but now that I know how hard you guys are working, I can say with certainty nobody will do worse than a negative 1/2 on my midterm. Have I given you any useful information? No. It's one of the jobs as a professor. Okay? You got to learn these things for yourself. Condition 2, is that helpful or useless in this case? Useless. So 2 always holds no matter what z is, as left-hand side is less than 0. All right, now we have to look at condition 3. Well, now we know that a is negative. So if a is negative, what can you tell me about 1 plus a over na? Yes? It's strictly less than 1. Could this be a negative number? No, because I'm dividing a by n sub a. So the worst this could be would be negative 1. And in fact, it can't even be as large as negative 1 because I've put in this factor of 100 plus 4 to just really protect myself. So over here, this right-hand side is strictly less than 1, but it's still positive. What does that do to z? So what is that going to do to z? Must be greater than 0. So if it must be greater than 0, and it has to be either 0 or 1, it forces z to be 0. As right-hand side is between 0 and 1, forces z to equal 0. Thus, if a is less than 0, that implies z equals 0. Yes?
Well, the saying that in case 2, condition 2 is useless, kind of, to me, gave the wrong impression first. It's useful, it's consistent. It would be really useless if condition 2 accidentally forced z to be 1.
We're into a semantic point here. The way I look at it is when case 1 holds, condition 3 is along for the ride, and condition 3 does not have any role in the value of z. When we're in case 2, condition 2 has no effect on z, it's just along for the ride. Okay, so this is the very first, you should have by now read all of this stuff in the chapter on how to get all these conditions in the confines of integer linear programming. Okay, so this was a little bit more time than I wanted. I don't mind doing this because this is extremely important to see how you can phrase all of this linearly. Okay, so I want to make sure that this is clear and that we've seen we can now introduce a variable that will detect whether or not a certain condition happens. So think of it as I want a certain critical threshold. One nice thing might be if you do a movie theater, if the demand exceeds the capacity, you want to know, right? You cannot sell more tickets than seats. All right, well, what companies sell more tickets than seats? Airlines. All right, but for a movie theater, you do not sell more tickets than seats. For the most part, you don't have people who are no-shows to a screening of a movie. This is different than the airlines, where I still don't understand how you can have so many people who don't show up for a flight, but this happens. Okay? So in this situation, we now have a very quick way of detecting whether or not a certain quantity is at least a given value. Okay, any questions about this? All right, so this is the first of many different ones we can do. The next one is the OR statement. Okay. Any questions about this? Yes?
Yeah, so my question is, for condition 2, you're saying that Z is, so, sorry, in case 2, when Z
Okay.
is 0, then A,
Oops.
0 is less than or equal to 1 plus A over NA, but I thought we just said that it can never be 0. Then you can never get 1 plus A over NA to be 0.
We're talking about this?
Yeah.
Right, I have Z is less than or equal to this expression.
Okay.
You know,
Does it matter that you can never be 0?
right, if A is negative, so let's say A is -5 and A is 100.
You get smaller and smaller, but you never actually.
Well, I'm saying this is going to give me a number that's less than 1. It'll still be positive. So I now have Z as a number that's less than 1. Z is less than a small positive number. And the only integer among 0 and 1 that's less than 1 is 0.
Yeah, I was being thrown off by the less than and equal to, but
Right,
it's not.
right. So it corrects itself. And so you have a condition that initially there's a lot of different possible values, but because we know Z is either 0 or 1, these conditions then improve. And that's the whole thing, is Z is either 0 or 1. So as you're going through all of this, okay? All right, any questions on this? All right, so I think we have time to do one more. Can I erase this part over here? I want to try to keep the conditions here. So you can see now why it's convenient to introduce, a little bit of extra stuff over here. It allows me to write things a little bit nicer without putting in factors of 2 and whatnot over there. If I'm going to choose a bounding quantity, let me just choose a really large bounding quantity. All right, so let me do an OR statement. And let's be exclusive. So condition 1 is I want ZA to be in 0, 1. Condition 2, I want A over NA plus delta over 2NA to be less than or equal to ZA. And in condition 3, I want ZA to be less than or equal to 1 plus A over NA. What does this remind you of? What does this remind you of? The one we just did, right? So this is what we just did a moment ago. So when we're doing the exclusive OR, what we're going to do is we'll get exactly one of A greater than or equal to 0 and B greater than or equal to 0 holds. So over here, this is going to give me ZA is equal to 1 if A is greater than 0, greater than or equal to 0, and 0 otherwise. So ZA equals 1 if A is greater than or equal to 0, ZA equals 0 if A is less than 0. Condition 4 is ZB is in 0, 1. Condition 5 is B over NB plus delta over 2NB is less than or equal to ZB. And condition 6 is ZB is less than or equal to 1 plus b over nb. What does this give us? Same thing now with z's, with b. So now it gives us zb equals 1 if b is greater than or equal to 0, and zb equals 0 if b is less than 0. So it's time for the seventh constraint. I want exactly one of these two to hold. I want either a to be greater than or equal to 0, or I want b to be greater than or equal to 0. What can I do to force exactly one? You're so close. It's not see if they're 1. Add them and force them to be 1. If I force them to be 1, then that means either ZA is 1 and ZB is 0, or ZA is 0 and ZB is 1. So this forces exactly one of these two conditions to hold. And then if you put these in as your constraints, if you now have a choice of all your variables and somehow both A and B turn out to be negative, it will not be feasible. It's going to force at least one of them to be greater than or equal to 0. And it will not allow both of them to be greater than or equal to 0. Okay, so this is the exclusive OR. We have been taught that it's not good to be exclusive, right? We're supposed to be inviting, you're all welcome to join us on Sunday to build the no, I'm sorry, we're not building the supercell, right? We're building Evil Lord Businesses layer. So we don't want the exclusive OR. What kind of OR do we want? The inclusive, right? We want it to be inclusive. We want, instead of exactly, we want to play exactly with what phrase? At least. I need to add one line. What do I do? Yeah, all I do is I add a diagonal line like that, and we're done. The advantages of being on a chalkboard. All we do is we change condition 7 to be, oh, sorry, did I do it the wrong way? Yes, you have to draw the line the right way. That makes a difference. Sorry. And now, that forces at least one of them to be 1. Can they both be 1? Yeah. Sure, more the merrier. If they're both 1, that's fine. But at least one of them has to be 1 now. And so now this gives us the inclusive OR. So we're beginning to see a lot of the things that we can do with integer linear programming. All right? So this is some of the beginning things. Okay, we've got 4 minutes left. That should be enough time to do maybe one more. All right, let's do if-then. All right, so at this point, I'm going to assume now that we're fine with all the conditions over here. I'm going to erase this just for the space. So if you think about programming, look at the words we're now allowed to use in our discussions. Or, exclusive or, if-then. What about and? Do you think we have and? Do you think we should be able to get and from stuff like this? Yeah. So this is now like elementary truth tables. So if we want and, we just want ZA to be greater than or equal to 0. We want ZA to be 1 and ZB to be 1. Okay, just look at them individually. And is not difficult to do. It's the or that's part of the if-then. So if-then. So I'm going to do the following. We want, and there's lots of different ways that the following. If A is less than 0, then we're going to want B to be greater than or equal to 0. And the conditions are the following. 1 is Z is going to be in 0, 1. 2, n sub A will be greater than or equal to A. 3, A plus 1 minus Z of n sub A will be greater than or equal to 0. And 4, B will be greater than or equal to negative Z times n sub B. I think this should work. All right, so when we do something like this, there's going to be 2 cases as always. What's the first case? So when we're doing something like this, what's the first case? Yes?
The first thing that a is less than 0.
Okay, so we could do a is less than 0. So if a is less than 0, this is going to be no problem. So did I drop a typo? Oh, it's an a times z. I know there has to be a typo here because if there's no variable in play, why would that constraint be there? So imagine a is negative. Does this give me any information about z? No. If a is negative, this is a negative number, I need this expression to be greater than or equal to 0. What does that tell me about z? Well, if a is negative, I need this whole expression to be greater than or equal to 0. What must be true about z? Z has to be 0. If z equals 1, then I would have a plus 0 is greater than or equal to 0. That's false. So case 1, a is less than 0. 2 does nothing. 3 makes z equal 0. I'm sorry, makes z equal 1. Right? If a is negative, the only way equation 3 can be satisfied is if z equals 1. What about a... I'm sorry, 0. No, I was right first, sorry. So it forces z to be 0. And what about condition 4?
Hopefully this makes it 1.
Well, if z equals 0, then we have b must be greater than or equal to 0. And then 4 makes b greater than or equal to 0, which is exactly what we want. And now we would just go through and say, well, if a is greater than 0, according to the logic tables, if a is greater than 0, it doesn't really matter what happens. So I'll leave that to you to think about what would happen there. But we've seen over here that the only way this is consistent is if a is negative, it's not consistent unless b is greater than 0.
So
We've got to stop now, unfortunately, because it is 1 minute past. So if you want, by all means, feel free to ask a question, but I know some people have to get